Uh, Pritam Kumar Shahi, can you just okay? Yeah, because there was some noise. Anyway, mm, yeah. So, can you just confirm? 1 second.
Yeah, it is audible, sir.
And my screen is visible.
Visible.
Okay. So we will wait for a minute or so if anybody joins. Otherwise, we'll start.
Yes.
So Pradeep and Pritam are here. Oh, Pritam left. I should not have taken his name, I guess. Anyway, uh, so okay. Uh, Actually, this is the problem. When people get the session recordings and slides, they don't join live, is what I've
Yeah.
observed. Anyway, can't help it. Okay, so we'll start. It's already 6:05.
Let us wait for some time, sir. Let us wait for some time.
Pardon? Did you say
Let us
anything,
wait for
Pritam?
some time.
Pradeep?
Let us wait for some time, sir. Maybe people will come for 5 minutes more.
Okay, okay, we'll wait. Yeah, somebody joined. Buditi.
Abhijit.
Uh, 1 second, I'll see. Yeah, I think it's better if we wait for a couple of minutes. I think some people are
That's
joining in.
yeah.
Yeah, so okay, I'll modify this one. Yeah, I think this is more uh, apt. Anyway, so those of who are here, have you had a chance to go through the lectures of Professor in this week's content or not yet?
Well, we have done, sir. I just like that. We completed the assignments actually. Today was the last. Yeah, tomorrow is the last date, so we submitted the assignments.
So you have seen the lectures and you have submitted assignment also.
Yes, sir. Yeah, two assignments we have submitted so far.
Yeah. So actually, ideally, this lecture should happen after the deadline for the assignment. But yeah, there are some issues there. So in any case, we won't solve the exact problems which are in the assignment, so it should be fine.
It will be busy, sir, actually solving their problems. Maybe.
Yeah. So were you in my first class, Pradeep? Were you there?
Sir, actually, you're discussing many things, actually, so just
Okay.
uh,
So the thing is, uh, I don't directly solve all the problems or directly jump into that, because I personally feel that if you understand the concept and maybe some variations of that problem, you will solve that on your own anyway. So typically, I discuss some problems and some concepts also. So
yes, actually, yes. Actually, you're discussing, sir, this free velocity and all, actually, sir. Free
yeah,
velocity,
last,
etc.
last time we
Yeah.
discussed that.
Then that you give example of how it will happen in case of turbulent flow and all. Yeah.
Yeah, maybe maybe that was ahead of the syllabus, but anyway, somebody had asked, so I thought I'll explain. That will come later also. I think.
And then rho VD by mu, rho VD by rho VL by mu, something. Though you're discussing those things.
Yeah, yeah. So I think.
Reynolds numbers are. I think you ended there. So Reynolds number probably you ended there.
Hmm. So I think it is 6:10. So I think we'll start. Let people join.
Yeah.
So yeah, welcome everyone. My name is Akshay. This is the second class, and it is regarding discussion on the topic which is fluid statics. Uh, and I hope this discussion will help you in solving some of your assignment problems. So basically, uh, as the name suggests, uh, fluid statics is nothing but a branch of science, or maybe a part of fluid mechanics, which deals with the fluid in static. So what does it mean? Uh, so in simple words, when you say something is in static condition, that means there is no relative movement between the molecules of that particular, let's say, fluid in this context, or maybe solid or something else also is okay. So, so on that line, when you say fluid statics, that primarily deals with the fluid at rest, and not only that, there are some cases wherein we deal with fluid that appears in motion, but it is not having any relative velocity or relative motion amongst its own molecules. So maybe we'll see some example about that also. So let's get started. Uh, just a second. Yeah. So can anybody tell me what is uh, pressure? If anybody
The
asks you, if in
force per unit area, sir. Force per unit area.
okay, that's the formula for it. But mm, okay, acceptable definition. So in the context of fluid mechanics, when we say pressure, it is basically uh, uh, I'll just write it down because these. Oh, 1 second. So when you say pressure, it is uh, always normal force, or maybe uh, force per unit area. But this force acts in normal direction, so it's always perpendicular.
So,
Uh, so force per unit area in normal direction, because uh, the force can act in different directions on any plane or surface, but we consider pressure as the normal force. And
But sir, there is something, some static object is there, and something hits it from side or from some angle. Then in that case, what will happen? How it will happen? Like it laterally it will hit something.
so first of all, that is not pressure. That is maybe called as impact force or maybe impulse or something. So
All
in
right.
that, it can be in different directions. There is no problem there. Uh, so so since we are discussing fluid statics, we have to discuss pressure because you know this is very famous. This thing, right? Pascal's law. So uh, Pascal's law basically deals with what it says is when your fluid is at rest, pressure is same at all points in the fluid. So that is the Pascal's law. I hope you know that. And more important than that, okay, first we finish the pressure. So pressure, the definition is like this, and you should know some more things about pressure. Uh, Pressure is scalar uh, because it is always incompressible. Sorry, but I mean before I should put as a scalar thing. First, I should mention that pressure always is in compressive in nature. So when you say some pressure is exerted on something, it will always try to compress that thing. It won't be tensile or elongation. So that is not a force. That's a tensile force. And therefore, in a this thing, uh, as per the Pascal's law, when the fluid is at rest, it has no direction. It is same at all points, right? So you can assume that it is having no direction, particular direction. So it is not a vector. So it is a scalar. So therefore, pressure is also defined as pressure is a scalar quantity. Uh, and uh, there are like standard units for defining pressure. One is Pascal. Uh, then there is something called as bar. Then there is something called as torr.
But
Then there
sir,
is
it is always normal. So it is having direction, is it not? Vertical direction.
pardon.
Now, since it acts normally, pressure always is normal to the
Uh,
object. So
uh,
it should have direction also, is it not?
so this I should be like careful with defining this. When I say it is a scalar, that is only valid for statics. Uh, so it's a scalar quantity, and I am talking about uh, inside the fluid domain. Okay, when this force is exerted, it will be at the wall or gate or something. So when it is compressive in nature, it is inside the fluid domain. So for any fluid particle in the fluid, it is always compressible. But when you consider fluid hitting the wall, there it will exert a pressure which will be normal to that wall or something. Understood?
Yes, sir. Yes, sir. My question is, sir,
Okay.
is scalar because you're having pressure like, sir, it is always normal force per unit area, and it's normal force. So anything
Yeah.
normal
So
means
force,
it is having direction.
force will have the direction, right? That pressure, it will exert some force on that area, and that force will be normal to uh, the that area, whichever area, whether it is curved or straight, doesn't matter. Pressure will be compressive, but the force that is exerted because of that pressure on that surface, that will be along the normal direction, and it will always try to exert the force in a normal direction. So don't get confused between pressure and force because of that. Pressure is scalar, but force is a vector.
Sir, yeah,
Uh,
yeah.
and yeah, so there is one very famous question that for a static fluid, or I mean for any point inside the static fluid, what will be the Morse circle diagram? So those who don't know what is Morse circle, it is basically used in solid mechanics to determine the resultant stress acting on any plane at any angle or something, at any angle or any orientation. So it is typically a two-dimensional graph wherein on x-axis you plot uh, normal stress and on y-axis you plot shear stress. So depending on depending on how much normal stress uh, and how much shear stress is applied on a particular location in a solid, you draw a, a Morse circle diagram, and typically it looks like a circle because you can uh, you know uh, uh, you can have different like I cannot go into depth of it because this is a fluid mechanics class. But the point that I'm trying to make here is when this type of question is asked, it is actually a combination of fluid mechanics or fluid statics and solid mechanics, which is deals with Morse circle diagram. If you know, that is fine, but if you don't, that is also fine. The thing that you should remember or note down is on x-axis we plot normal stress and on y-axis we plot shear stress. So now, as I mentioned that let's consider any point or maybe some fluid domain like this. So at any point inside the fluid, let's consider this point. If you see the direction of pressure, it is always compressive in nature, right? So it will be exerting force, pressure like in this direction, always compressing it. So, and since this is a fluid at rest, there is no relative motion between the particles. So there will be no shear stress. So now we know that this tau axis or y axis, it will be zero value. So our point or Morse circle diagram, it is essentially it can only be a line or a point. It cannot be a circle because there is no shear stress. Now the next question is when you consider normal stress uh, on the if you consider this as a origin, uh, to the left of the origin it is a tensile stress, on the right side of the origin it is compressive stress. So as we can see, it is a pressure is always compressive. So it will some it will be at any point on this side of the origin, and that will define the uh, you know uh, uh, the total stress will be equal to uh, the pressure. But since pressure is compressive, we have to show it as a negative sign here. uh, uh, 1 second. So this question is asked many times. I have seen in many competition exam.
Sir, it's not clear a little bit. Can you please repeat a little bit? Sorry, can you repeat a little bit? Why it is minus? So why it is
See,
tensile?
by the general sign convention, when your stress is tensile in nature, it is considered as positive, and when it is compressive in nature, it is considered as negative. That is a general sign convention.
No, no, sir. When tensile it is negative, I think.
Pardon?
When it is tensile, sir, it is negative, I think. It will.
No, 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 no.
Oh,
Tensile is positive, compressive is negative.
I see.
Uh,
Okay,
that's a
got it, sir.
universal sign
Got it, sir.
convention.
I
Yeah.
got it, sir.
Yeah. So this is very like I mean, if you say fluid statics, it's a quite interesting question that is asked on multiple occasions. So I hope it is clear. And then Yeah, so see, this Pascal's law is okay. We understand that that pressure inside a fluid which is at rest is always same at all points, but it has very important application. Uh, so I'll just draw a simple schematic of it. You might have heard, something called as hydraulics or something. I'll just like I'll just draw a simple. Pradeep, one request: when you are not asking, can you just mute yourself because some background noise is coming. Yeah, thank you. So what happens in many practical applications, you have a continuous system or domain, fluid domain like this, and what you do, for example, if you want to lift a car or something, so car is quite heavy object, and to lift the whole car, it's not uh, you know uh, easy, at least manually. So what you do, you can use the Pascal's law. So what Pascal's law says that, and this will be a continuous same fluid all throughout. So what happens? Here you have a, when you'll apply some force here on this small area, cross-sectional area A, and this is bigger cross-sectional area capital A. And what happens? This particle inside the fluid will experience the pressure because of application of force, and that pressure will be compressive in nature, and it will be force per unit area. And same pressure is transmitted throughout the domain at all points because the fluid is at rest, there is no relative motion in it. So at the other end, at the other end where the car is to be pushed up, uh, it will be same, pressure will be same, and that will be acting on this bigger area, and it can lift, you know let's say mass of the car is m. So what happens, uh, you apply smaller force. So for example, the force that you apply from this equation, you get mg into a by a. So I'm just reshuffling the terms. So here you can see this area, smaller area, small a is lesser than capital A, and you design it that way. Therefore, a by a will be less than 1, and therefore that force that you need to apply will be less than the total force that is required to lift the car. So therefore, this is like the interesting application of Pascal's law, where you can achieve lifting of something like car with lesser force applied at the other end of the device, which is shown here. So then sometimes they ask validity of Pascal's law. So they will try to trick. The question may be, for example, I'll just give a question. Uh, Pascal's law is valid uh, for. So there will be options like uh, compressible fluids. Then there will be option like uh, non-Newtonian fluids. This we discussed in the last class. Okay, this non-Newtonian. There are different types of fluids. One is called as like the major fluids that are observed on the Earth's surface are water and air. They come under the Newtonian class of the fluids. But there are some fluids which are non-Newtonian. You can go to the last class and see the notes or see the video. Then you'll understand what is non-Newtonian fluids. There are different types like Bingham plastic, thixoplastic, something like that. So there are 2-3 types which are non-Newtonian, and maybe another option could be uh, let's say viscous fluids, and maybe the option will be okay. One second. Last one can be incompressible fluids. So, can anybody give me the correct answer for this question? Anyone? Muditi or anybody? I'm just seeing the name and that's why I'm calling.
Is it incompressible, sir?
Okay, so we have an answer which says option number 4, incompressible. Anybody else wants to take a shot at this? Okay, so the thing is, the answer is actually all of the above, because Pascal's law doesn't say what type of fluid. It just says uh, fluid must be at rest or no relative motion between fluid particles or molecules, whatever you want to write. But the idea is Pascal's law, it is independent of type of fluid, or it is independent of compressibility or incompressibility. As long as the fluid is at rest or there is no relative motion between its particles, it is valid. So the answer, actually this question is wrong. The question should be if the fluid is at rest, then Pascal law is valid for what type of fluids, and the answer is all of the above. So uh, that was a trick there. Anyway, then there is actually, when I say fluid must be at rest, so everybody understands. So that will be a stationary fluid in a tank or maybe some container or something. But when I say there is no relative motion between fluid particles, so there is a different case that comes into the picture. So what happens? Let's say uh, there is a, or maybe I'll just write the title, container and fluid moving with constant velocity. Am I audible? Anyone?
Oh, yes, sir.
Yeah, actually, I was using Wi-Fi and it got connected in between. I'll just share my screen again. 1 second. Uh, yeah. So I hope my screen is visible again.
Yeah, yeah, visible.
Yeah. 1 second. Just this recording is going on, right? This meeting recording. Yeah. Okay. Yeah. So the thing is, sorry for the this internet issue. It was, I mean, it was not my problem or my this thing anyway. So the first case is when your container and fluid is moving with a constant velocity. So let's say it will have some velocity u. So in that case also, there is no relative motion between two particles inside this fluid domain. So Pascal law is valid in this case. Then there is a case where is wherein you say you have a container. 1 second. You have a same container, but in this case it is let's say if this is your okay, I should not use same color because let's say this was your initial level of fluid in the container, and then it started moving at a constant linear acceleration. So in this case your velocity was constant, and in this next case your acceleration is constant. So what happens when your vehicle accelerates at a constant acceleration, this liquid level will not stay horizontal. There will be change in the liquid level, something like this. So liquid will be shifting slightly to the backside because of the acceleration. Uh, Pradeep, can you just mute yourself for a second? It's background noise is coming. So in this case also there is no relative motion between two particles inside the fluid, and therefore we can assume or not assume the Pascal law is valid for this case also. But now the question can be not all motions are linear, right? Or in a XYZ direction. There can be some you know rotational motions also. So I'll just give you because if I draw that and maybe I can draw it, but see, I'll just give you two cases. So there is a container like this, cylindrical container. Please forgive my drawing, but that's not. One case could be 1 second. Yeah. So there are two cases in case of rotational motion. So one case is you have a cylinder, and it is having uh, what you call constant angular motion. For example, uh, uh, if this is its axis of rotation, let's say it is rotating about this axis, and if it is rotating with a constant angular velocity omega, so you will observe oh sorry, you will observe that the liquid surface will be assuming some shape like this. Okay. uh, Maybe yeah, I just this dotted thing indicates fluid. So when it is rotating with a constant angular velocity, you will observe liquid interface something like this, which is called as paraboloid shape in fluid mechanics terms. So in this case also, when the angular velocity is constant, there is no relative motion between the fluid particles, and you can assume Pascal's law is valid. But the last case, where let's say this thing is rotating about this axis with constant angular acceleration. So in this case, like there will be some interface like this or some maybe other shape. But the thing is, when something is rotating at a constant angular acceleration, then there is something called as Coriolis acceleration forces, and those forces make relative motion between the fluid particles. So therefore, the Pascal's law is not valid in this case. All other three cases where you have linear motion, where your velocity is constant, acceleration is constant, and even in case of rotational motion, when your angular velocity is constant, Pascal's law is valid. But if you have constant angular acceleration, there Pascal's law is not valid because of Coriolis forces. So please keep this in mind. This question is not yet asked in any competitive exams, as far as I know, but it can be asked in future. So when somebody says when the Pascal's law is applicable or valid, you can say when the fluid is at rest, or when it is moving with a constant velocity with its container, or constant linear acceleration, or constant angular velocity. And based on that, we'll take one example. Let's before that, just give me 1 second, because there is a small derivation to get the angle of this thing. When the fluid moves with constant linear acceleration, the interface shifts slightly to the backward when the fluid is moving or accelerating in the direction as shown in the second figure here. So by what angle this thing moves is the question. Okay. So for that, there is actually a very simple derivation. Let me just check if I find it, or maybe you can refer it in any standard book. But the formula that comes out of it is the important one. 1 second, I'm just looking for the derivation. Is it available with me at this point? Yeah, so basically, the derivation it goes like this. I'll just copy this image if I can. Okay, something is. Okay, anyway, I'll draw it. I think it is not copy pasting. So, actually, we are taking some more time than required. Anyway, we'll just move on with this. This is the last part here. So, earlier it was the liquid level was this. Sorry, it should cross at center. So, somewhere here. Let's say it is accelerating in this direction with constant acceleration. If the acceleration is variable, then also the Pascal's law is not valid. Okay, keep that in mind. Only for constant acceleration it is valid. So what you do, you take a small fluid element in this fluid domain, and you maybe you can just zoom in and see what happens there. So here, what happens? And let's say this end is at h1 height and this is at h2 height. So, and since this is a small elemental area, we'll consider its length as dx. So what happens? And let's say this angle, the angle by which the surface slanted, it's called as theta. So in that case, what happens? If you draw the free body diagram, there will be pressure forces acting on this element, and we are not considering gravity and other viscous forces because the fluid particles at rest. And since this element is horizontal, there is no gravity force variation along it. So as per Newton's second law, the sum of the net forces acting on this element will be equal to its mass. What area in horizontal direction is, let's say there is a pressure P and acting on this area A, and similarly P2 acting on the area A. P1 and P2 will not be same. Okay, if they are same, then the fluid interface would have been horizontal. Horizontal in the case of constant velocity, something like that. But here, since there is acceleration, there will be change in pressure. So, what is the net force in the x direction? It will be P1A minus P2A equal to, and mass of the fluid area fluid element is rho A, small length dx into ax, right? And by the law of hydrostatic, we know pressure is equal to rho gh. So you can write P1 as rho g h1a minus rho g h2a equal to rho a dx into ax. So if you just cancel this rho and a from both the sides, what you get? You get h1 minus h2 into g will be equal to ax into dx. And if you just rearrange the terms, if you write ax by g, it will be h1 minus h2 divided by dx. So now look at the geometry of the figure, and from geometry you can see this comes out to be equal to tan theta. So which is the angle by which your surface is inclined. So when you want theta, you take the tan inverse of ax by g. So if in another, I'll not go do the derivation of the second case where along with the acceleration in x direction, constant acceleration. What if there is constant acceleration in the y direction as well? So in that case, if there is ay also exists, so but this is constant, then your theta becomes tan inverse ax divided by ay plus g. You need to consider the direction of ay and g. If ay is in downward direction, it will be plus, and if it is in upward direction, it will be minus, because gravity is always downwards, right? So if you are accelerating upwards, your if you are accelerating upwards, it will exert more pressure on the fluids, so that time it will be addition. But if you are decelerating, or if you are accelerating downwards, then it will be minus. So just don't worry about the sign, because that will confuse you at this point, because we have not gone through the y-axis ay derivation. But this is what it is. So we'll take one question which is quite standard question in this context. So there is this YouTube type of thing. And it has wheels, and it is it is moving with constant acceleration. Just 1 second. Yeah. So it is said that this YouTube is moving in this direction, and the acceleration is constant, and the liquid I'll use different color for showing liquid. Liquid is showing so liquid level is like this in the YouTube. So the blue color represents the liquid, and it is given that this horizontal length is 1 second. So the horizontal length is 20 centimeters. This height is average height of this is 6 centimeters, and this is 16 centimeters. And the question is, you have to identify which of the following is correct. So this is the question, and I have seen this question maybe like in 2-3 places so far when I was preparing for this lecture. So maybe you should pay attention to this type of question also. So the question is, the tube is so the options are: tube is accelerating at 5 meter per second square. B option is okay. Can I copy this because the options are same? The second option is the tube is accelerating at 1 second. The tube is accelerating at 2.5 meter per second square. That is the second option. Third option is tube is decelerating. 1 second, I did a spelling mistake. It should be E. Decelerating at 5 meter per second square. And fourth option is same. Only the value is changed. Tube is decelerating at 2.5 meter per second square. So, can anybody answer this question? It is actually quite straightforward to what we did just some time back, this derivation of tan theta. But there is a small catch. Please, if you can catch it, that's a good thing. If not, we'll see. So the thing is, in all these cases, your objective should be to find this tan theta, and since this is exactly same as what we did it here in the derivation, the tan theta is basically ax by g, right? But here you have not given any ax or g. But the other thing is, from this figure you can calculate theta, right? If let's say if I join these two interfaces, so this will be the theta, right? This angle will be theta. So what will be the tan theta from the figure? It will be 16 minus 6 divided by 20, which will be 1 by 2, right? So, and we say that, this ax will be g by 2. So g is typically taken as 10 meter per second square. So the ax will be 5 meter per second square. But now there are two options where you have 5 meter per second square as the acceleration, option A and option C. So Pradeep, can you just tell me out of A and C which one will be the correct option that you feel by looking at the geometry of the figure?
Sir. A, sir. A.
No, that was the trick in the question. See, in this question, when the fluid was accelerating, liquid shifts to the back. Somebody posted Sharif. said D, E, C, E. Okay. C. C is the correct answer. Because if the liquid is accelerating, it should look like this. The figure shown here. But when the fluid will decelerate, it should the front part will be having higher height than the back end. Because let's say you are moving with a constant velocity. When you started accelerating, the fluid will feel the push, so it will go back. And when you apply the brakes for stopping, then the fluid will feel the force in the opposite direction. So it will be on the front side. More liquid will come to the front side, and therefore the correct option is option number C. Tube is decelerating at 5 meter per second square. So that was the trick behind giving this question. That typically what I have observed is many a times we study the acceleration case, but we don't study the deceleration case, and that's where examiners catch you in some competitive exams somewhere. Okay, so this thing is okay. Pascal's law is done. After that, you know, we go to this thing. This what you say, pressure measuring devices. There is a whole class of this thing there, devices there. But before that, can anybody tell me what is okay? I'll ask it in the question format. Which of the following is correct? Okay, so this is regarding the gauge pressure and absolute pressure question. This concept is also very important because many times we don't understand this, and if in any interview, if you get confused between absolute pressure and gauge pressure, trust me, it will not go good for you. So, okay, coming back, let's say absolute pressure greater than gauge pressure. So I'm giving you certain scenarios, and you have to tell me, instead of correct, I should say which of the following is practical or feasible, or maybe I should just say realistic. So first guess is, can the absolute pressure be greater than reverse of this? Can the absolute pressure be less than gauge pressure? And yeah, can the gauge pressure be less than 0? And can absolute pressure be less than 0? So this is a multiple choice question. So multiple options are correct, and maybe none of them are correct. So anybody? Sharif is typing. He says option A. Okay, option A. So you are saying absolute pressure can be greater than gauge pressure?
Yep.
Okay. What about the other options? First of all, tell me about the last option, the D option. Do you think it's practical or realistic?
Sir, it will go below, sir. It will go below the ground, something like that. Yeah.
Sharif says absolute pressure equal to 0. Buditi is saying A and C are correct. Okay, so yeah, I'll just draw the figure, and that will clarify this thing. So whenever you have confusion like this, it's better to stick with some sort of figure in your mind, because that way you learn clearly. So let's say this is a zero pressure. Pressure is equal to 0, and let's say this is equal to the atmospheric pressure 1 bar. So you know, this thing, gauge pressure, absolute pressure, they are defined with respect to the atmospheric pressure at that location. So if you are at sea level somewhere, then there will be atmospheric pressure of 1 bar. But if you are at some hill station, atmospheric pressure may not be 1 bar. So it's not correct to write the value here. I'll just write the atmospheric pressure, which is locally available there. So one second, I'm just you know uh, how should I say this? I'm just looking at explaining this thing in a crisp manner. So basically, this gauge pressure, as the name suggests, it is a pressure shown by any gauge. And in earlier times, there were gauges which were used to show, get the pressure thing, but they were not giving you the exact value of pressure. What they were giving you is the value of gauge pressure with respect to the atmospheric pressure. So uh, gauge pressure can be uh, there, or gauge pressure can be this also. So gauge pressure, uh, one second, maybe I'll use some another type of color so that you'll understand. Let's say I use blue for gauge pressure. So gauge pressure is always defined with respect to the atmospheric pressure. So if at any location your pressure is uh, more than the guys, one second, I'm getting a call, one second. Yeah, sorry for the interruption. There was an emergency, so I had to take the call. Anyway, coming back to the discussion. So yeah, gauge pressure is always defined with respect to the atmospheric pressure. Gauge pressure can be more than the atmospheric pressure, or it can be less. Uh, and absolute pressure is, it's an absolute value. So, as you said, absolute pressure is always greater than gauge pressure. That is correct. Absolute pressure less than gauge pressure. No, that is not correct. And gauge pressure can be negative. As I said, it is with respect to the atmospheric pressure. So it can go below atmospheric pressure, which is called as vacuum. You must have heard this term somewhere. So in outer space, when you go, they say it is a vacuum. So there, the gauge pressure is minus 1 bar, and absolute pressure is 0. So gauge pressure can go below 0, but absolute pressure can never go below 0. It can be equal to 0 in theoretical or very highly idealized case, but it cannot never be go to negative value, and this is also wrong. So option A and C are correct. I think some of you have mentioned this in the chat also. Just 1 second. I'm not able to see the chat. What happened now? 1 second, guys. Yeah, so this thing. Buditi has given correct answer, and I think Sharif also correct answer. Okay, so this is very important concept going forward, because whatever measuring pressure measuring devices that we are going to see here, they typically give you either gauge pressure or differential pressure, something like that. And one more interesting question that is asked in some other
Sir,
exam.
but is there any message, sir, like any pressure measurement should include atmospheric pressure also, is it not? Like any gauge pressure should also include the atmospheric pressure together. Like you are measuring pressure means you should actually measure the gauge pressure plus atmospheric pressure together.
Yeah,
It's
so
not.
that is gauge pressure plus atmospheric pressure is your absolute pressure. So
Yeah.
therefore, absolute pressure is greater than gauge pressure. Therefore, the first option is correct.
Now my point, sir, in the space, sir, there is no pressure. It is.
Yeah. In space, there is no pressure. Therefore, absolute pressure is 0, and that means your gauge pressure will be equal to minus atmospheric pressure, right? So gauge pressure can have negative values. That is a takeaway. But absolute pressure cannot have negative values. When your gauge pressure has negative values, that means your system is under vacuum condition. Outer space is full vacuum, but there can be some containers where you maintain maybe 0.5 times of atmosphere vacuum, something like that. Actually, currently I'm working on one experiment where we maintain one container at 1 kilopascal pressure absolute. So that will be minus 100 kilopascal gauge pressure. So that also is possible. Understood?
Sure. Yeah.
Yeah. So yeah, there is this thing called as maybe not a question, but it's a you know we don't have that time to go into the details of this, but there is something called as hydrostatic paradox. You guys can look into it. Uh, so it's actually very counterintuitive. What it says is, uh, let's say, have you heard of this hydrostatic paradox? Anyone? I think it is in some textbooks also. If you have, just let me know or maybe type it out. If you haven't, I'll just briefly explain it. But
We have not. We have not gone through. We have not.
okay, so what it is basically, let's say you have a this thing. Okay, let's say you have some random shape like this, and you fill liquid till this level. Let's say water, and you put one pressure gauge here on the not on the top actually. There it's atmospheric pressure. So this is the free surface symbol. So inverted triangle, if anybody shows on any surface, that means it's a free surface. So there will be no shear force. There is only gravity or normal forces there. It's just a symbol. And then there is some container like this, and there is some container like this. Please forgive my drawing, but 1 second. all of them are at the same base level. Okay, so these are same levels, ground levels, and fluid is filled till the same height in each of them. So this is the free surface. Okay, so now if you put some pressure gauge at the bottom of all these three containers, and if you see the pressure, what you will observe is, let's say I'll denote them by numbers, and let's say this height is same for all, and all of them are at rest. Okay, there is no motion or something like that, because we are discussing fluid statics. So what you observe is E1, I mean at bottom, pressure for first container is equal to second, is equal to third, and that is equal to rho g h. Assume that it's water. All containers have same liquid, and then but in case of first fluid, you know, the force exerted at the bottom, let's say F1 is equal to you know, weight of the I'll use some symbol for it. Let's say weight of the water in a container is denoted by W. Okay, just the symbol. So what I mean is where this paradox comes into picture is, see, what you see is pressure is same in all three cases, but when you do the force calculations, what you observe is, in case of first liquid, first container, uh, weight of the liquid in the container is greater than, sorry, in case of first, it is equal to the net force at the bottom of the container. In case of second liquid, uh, weight of the liquid is greater than the force at the bottom. And third, what you observe is this weight of the liquid in the container is less than the force at the bottom. Assuming, see, the assumption here is this bottom area, all of them have same area. It may not look like in the figure, but assume that we have constructed those containers such that they have same bottom area. So see how you calculate force. Force is actually F1 will be P1 into A1, right? And F2 will be P2A2. But A1, A2, A3 are same. So, and since pressure is also same, the forces F1, F2, F3 are same. But what you observe here is, see, the all force will be same only, F2, F3, and they will be equal to this pressure into area. So, you can denote this as a P. So, where the hydrostatic paradox lies is where you have this different containers of irregular shape, but same base area, and there you observe that pressure is same at the bottom on all containers, but in one container you are putting more liquid, in other container you are putting less liquid, but you are getting same force on the bottom. So this is very counterintuitive, and this is what is called as hydrostatic paradox. Uh, so this will not be asked in some, like, there will be no numerical on this, but in some interview they may ask you, how do you justify hydrostatic paradox? So there is an explanation for this. If I'll just give you a brief idea. maybe you can read up upon it, but the explanation is, see, in the case of first container, there is no doubt, okay, whatever weight of the water is in the container, that is exerting force at the bottom, which is equal to pressure into area. But in case of the second liquid container, if you consider one point on the boundary of the container inside the liquid, you can see there will be pressure force acting normal to that point, right? In this way. So if you resolve these forces into x and y direction, so you will get something like that. No? Oh, 1 second. It should be the opposite way. The fluid exerts force on the container, and container exerts, because of the Newton's third law, the container exerts force on the liquid. And since this system is in equilibrium, that forces will be equal and opposite equal in the magnitude and opposite in the direction. So this container exerts force on the liquid in this way. So if you take the components of the force, the horizontal components get cancelled out because they are in the opposite direction. But in case of vertical components, they are unbalanced. So whatever is the extra weight of the liquid that is in these parts of the container, that gets balanced by the normal reaction, not the normal reaction, the vertical reaction from the container surface. And that is why this additional weight does not affect anything on the force exerted at the bottom. And same is applicable for the third case also. In this third case, the directions will reverse. So I know this is difficult to understand in such a small duration of time, but since we have constraint of time, I'm explaining it in brief. You can read up upon it. It's easily available in YouTube and all. So that is there. And one more simple question. Actually, this question. Anybody has any question on hydrostatic paradox? Should I go ahead? Okay, I think nobody has any question. Anyway, so
And you said it is a bit confusing, definitely.
yeah, I would advise you just take some time and maybe you can watch some tutorials on YouTube.
Yes,
I
you
checked
can.
I
That
checked it.
will, that's why we are silent, actually.
Okay,
Yeah.
fine, fine. So we'll move next. So this is very actually one very common question is there, but I have seen many people get confused in this. So there is a simple device, pressure measuring device, which is called as barometer. Okay. So barometer is nothing but pressure measuring device. It's one of the starting devices, like initially, started before all these manometers and all. So there, what happens? It's actually a practical observation. I'll just give me some like yeah. So barometer something. It looks something like this. Again, you have okay. This is very bad. Let's say you have some typical fluid container. This is the fluid level. What you do, you take a tube, normal tube that you get in the lab, and you dip it in the opposite direction in the liquid. So what you observe is, uh, you know, the liquid rises in this U-tube, inverted U-tube. This is what barometer is actually. There is no special thing there. Uh, and what you do actually, you have some outlet here initially. You evacuate the tube. There is no air or anything, and you just close it afterwards. So what happens? What is observed is this: uh, the liquid in the container rises up to certain height. Let's say h. So the question is, and let's say this is open to the atmosphere. There is no other complication there, and there is like vacuum at the top of this. In this area, there is very low pressure. Not low pressure, it's vacuum basically. So what happens? The liquid rises. Now the question is, what is H? So here you use the fluid hydrostatic law to measure the pressure, atmospheric pressure. So one key thing that I've observed is where like the whole point of asking this question was this only. So everybody, like most of the students who study fluid statics or fluid mechanics, they know what is barometer, or they have heard somewhere. But where they get confused is, I'll give you 3 points. Let's say uh, point number 1 is here, point number 2 is here, point number 3 is on the surface, and let's say point number 4 is inside the liquid down somewhere. I hope this is, I mean, you guys can see this. Is it too small or can you see this?
So it's fine, sir.
Okay. So the question is, typically what question is asked is uh, this thing. Mention pressure at P1, P2, P3 and P4 in increasing order. So can anybody tell me what will be the increasing order of pressures? Anyone? You can type it out also. I am seeing the chat in my mobile also. So see, P3 should be no brainer, right? P3 is equal to atmospheric pressure. Now, since you have studied fluid statics, you know, as we go down in a liquid, pressure increases, and that increases uh, by the amount rho gh. So this hydrostatic pressure, you know. So if you consider point number 4, and let's say this height was h dash, or maybe I will use some another alphabet. Let's say A. So in that case, P4 will be P ATM plus rho GA, correct? Because you are going in the fluid, so pressure increases. So P3 and P4 are okay. People get confused. I mean, what I have observed is many times people get confused between 2 and 3, and 1 is always there. So you should always remember from, let's say, this hydrostatic paradox case also, the shape or size of the thing does not matter. So why people get confused sometimes is this point number 2 is inside the tube, right? And point number 3 is outside, open to the atmosphere. But as long as this whole assembly is at static or rest, there should not be any pressure difference as long as the height of the points are same. So you can see point 2 and point 3 are at same height. So therefore, P2 will be equal to P3. There should not be any confusion there. People typically get confused there. And as I told you, this one is evacuated. This top surface is evacuated, and therefore there is, let's say, very low pressure there. So uh, you know this liquid level is rising, right? So basically, when it comes to the equilibrium, the pressure at this P1 point will be atmospheric pressure minus rho g h. H is the, let's say, h is the height till that one point. So therefore, P1 will be less than and P3 is atmospheric pressure. So P1 will be less than P3. Therefore, the correct answer is P1, P2 is equal to P3 is less than P4. This is the highlight, or this is the trickiest part of the question that you should remember. P2 is equal to P3. Many times people don't, they don't understand that and they get confused here. So that is one thing. Yeah, then we'll solve one problem where uh, like, see, in this course, there are different pressure measuring devices. So I'll just give you a brief classification for that. So if you consider pressure measuring devices, see, nowadays, so there are different type of devices. We are not discussing all of them. We are discussing only those who are using some sort of fluid statics or fluid mechanics for their operation. And if you do that, you see two types basically, and those only are of our uh, importance in this course or maybe for problem solving. This is simple manometers. And differential manometers. So simple manometers will always give you gauge pressure. Then you need to consider the atmospheric pressure at that location, and then you'll get the absolute pressure. And these guys give you only the pressure difference between 2 points. You don't get the absolute or gauge pressure here. So that's why they are called as differential manometers. Then there are two types in this. One is called as U-tube differential manometer, and one is called as inverted tube. You can put differential manometer. Okay. And here there is something called as piezometer, and there is something called as typical U-tube manometer. So I'll just see. Actually, we are running low on time because there are other things to discuss.
Sir, can I ask a question? Sir, what is the difference in piezometer, barometer, and manometer?
Okay. The last one is which manometer? U-tube manometer.
But no, sir. This piezometer, manometer, and barometer. So the three terms.
Barometer is like this. Okay. Barometer you use for measuring local atmospheric pressure at any location. Understood?
Yeah, yeah.
Whereas piezometer, it looks something like this. There will be a pipe through which your pressure or your fluid will be flowing. And what you do, you just take out a tube like this and you let it's open to the atmosphere, okay, in case of piezometer. So there will be some pressure inside the pipe and you let that fluid come out till some level. And whatever this height is there, H, that is your gauge pressure. So at the top, what you get basically is the pressure inside the pipe minus P atmospheric pressure will be the rho gh. So here you get the gauge pressure, right? Because this is atmosphere plus some rho gh value, and the rho is the fluid flowing through that pipe. This is the cross-sectional area. So in case of piezometer, it gives you gauge pressure, and the disadvantage is you cannot, this piezometer cannot measure negative gauge pressures, right? If you're if in a pipeline or somewhere, if the container is at, let's say, uh, 50 kilopascal or something like that, you cannot use piezometer, because when you open it to the atmosphere, the atmospheric air will go inside, and eventually everything will be at the atmosphere. So this piezometer is only usable if your pipe is at pressure which is higher than the atmospheric pressure. And one more thing, you cannot use it for gases, because if the gas is there, then if you open it to the atmosphere, it will just go out, right? This is only used for liquids. And if your liquid flowing through the pipe is having very low density, then you will have to provide very high pipe, or this H will be very large because rho g H is there, right? So to see the significant variation, you need high H, so that becomes a problem sometimes. Whereas manometer, it looks something like this. You have a pipe with some pressure P. Then what you do, you put something like this kind of thing. And what you do, you put some another type of liquid in between. So this blue line represents another type of liquid. It can be mercury, it can be water. It depends upon your application. So in this case, it is advantageous because now you can measure negative gauge pressures also, as long as this mercury doesn't go inside the fluid. That care you need to take when you design the U-tube. And you can use it for gas also, so there is no problem there. And since mercury is having very high density and very low vapor pressure, the deflection will be not that high, so the vertical limb of the U-tube manometer is also not that long. So U-tube manometer is a suitable choice, or better alternative to the this thing, piezometer. And yeah, and in case of differential manometers, if I just show you like this, so as the name suggests, differential manometers, they will give you a difference between, let's say you will have some pipe A and pipe B. So what you do, you take out the bleeds from both of them, and you connect some U-tube like this, and you put mercury inside it, and then depending on the deflection between these two levels, you get the delta P. So basically you will get PA minus PB equal to rho G H. This will be your H, and this is something like mercury. And when you say inverted tube manometer, differential manometer, instead of U-tube like this, you just put it in the vertically opposite direction, so ulta. So in that case, you don't put mercury in, you put very light fluids like air or gas inside there. So like that. So am I clear? We'll take one example for this. That may be a good idea, because it's actually many a times if these questions are asked in GATE and competitive exams. Uh, so I'll take one example. Uh, so this is a two question example. Okay. So okay, so you have a U-tube, but it is having not two branches. It is having three branches like this, and all of them are open to atmosphere. But you know, there is mercury filled in this part. There is mercury, and here you have some water also filled inside. This is water. This is 27 centimeter, and then let's use some another color. So this yellow color is there. So there is some unknown liquid. Oh no, there is this oil. It is oil with the specific gravity of 0.78, and its height is unknown. How much height is? So that is H2. I hope this yellow color is visible because we are out of the colors.
Yes.
Yeah. So and this mercury, some dimensions are given. This is 8 centimeter. This is 5 centimeter, and this is unknown. So this is H1, and this is mercury. So now it is a two-part question. Uh, first is what is H1 and H2, and second is if specific gravity of mercury is 13.6, 1 second. Oh, actually, this question is what is H1 and H2. That was in two parts. I written both of them here only. 1 second. I have written the whole question, but I forgot to. 1 second. Yeah. So, what is first of all? Can anybody tell me what is specific gravity? When I say specific gravity, uh, actually we are running low on time, so I'll only tell. So it is a density of any fluid with respect to any reference material. So for liquids, we use water density as a reference, and for gases, we use typically air as the reference. So water is typically taken as 1000 kg per meter cube, and air is 1 kg per meter cube, 1.1 or something. But typically you can take one. So when we say specific gravity of mercury is 13.6, the absolute value will be 13.6 into density of water, which is 1000. So it will be 13,600. So like that. So now coming to the question. So this is a classic example of this thing, application of fluid statics. So what you do, you consider this baseline, then you calculate the total pressure in all the limbs. So for the first limb, let's say I'll number them 1, 2, and 3, right? So in first limb, let's say this is a P at bottom, PB. So you start from the top. So at the top it is atmospheric pressure. Then you have water column of 27 centimeter. So rho of water, G, H of water. Then you have mercury column of H1 height. So row of mercury, let's say M. I'm denoting it by M subscript. And then you have H1. And that will be equal to your bottom pressure, right? And then you have second limb in which you only have mercury. So P atmosphere plus rho of mercury into G into 8 centimeter is there. So we'll just keep it in centimeter. We'll see. If required, we'll change it. And that will be equal to the pressure at the bottom line. For third limb, it is atmospheric pressure. Then you have some oil of specific gravity 0.78. So its density will be 780. So you have, let's say, oil of rho O, G, and its height is unknown, right? H2. That is also unknown. Plus we have some mercury of 5 centimeter. So then we add mercury G, and it is 5 centimeter equal to the pressure at the bottom. So now we have three equations, and we have how many unknowns? H1 and H2 are unknowns. So what you do some algebra, and what we can do is okay. So let's consider equation number 1 and 2, or from 1 and 2, what you get, uh, this row of water into G into H of water plus rho of mercury into G into H1 is equal to rho of mercury G into 8. Okay, I hope this is understandable. I'm skipping one step here because it is very understandable that we are, we are eliminating PATM and PB from the equations, and we are just taking whatever is the difference. So here rho of water is 1000, and G is also common to all, so we can eliminate G here itself. H of water is 27 centimeter plus rho of mercury is this much into H1 is unknown, and rho of mercury is this much to 8 centimeter. Here you can see only unknown remaining is H1, and that should be equal to 13.6 into 8 minus 27 divided by 13.6. I'm skipping some steps here, but you can do the algebra. And if you do that, what is it? 13.6 into 8 minus 27 divided by 13.6. So you get I'm 6.05 centimeter. So that is the answer to your first question. And from 2 and 3, it is also same only. Here the unknown will be H2. So what you do? Rho mercury G into 8 is equal to rho oil G into H2 plus rho mercury G into 5 centimeter. So here also you cancel GG because it's common to all. And then H2 will be, from here itself you can write, H2 will be rho M 8 minus 5 divided by rho O. So that is again 13.6 into 3 divided by rho O is 0.78, I think. Yeah, so 0.78. So if you do that calculation, 13.6 into 3 divided by 0.78, it is around 52 centimeters. Yeah, so this is how you do the calculations for these type of questions. Okay, you will find a lot of variations of these questions in this thing, in multiple exams or many subjective exams also. So I hope you can solve them. The only trick is in all this type of question is to find a level where you can, you know, where you will have same pressure on the both sides, and then you just start from one end and do the calculations. Uh, Actually, I can take one more example from here, but then our time will be over, and we have this other type of problems that is still remaining, which is called as buoyancy and flotation. Actually, this fluid statics covering it in one class of 2 hours is very difficult because there are a lot of things here. So, what you guys want to do? Should we go to the next part, or you want to take one more example of it? I think this is understandable, right? This fluid statics and manometers part. I think we can go to the next part where you have this thing, force balance and all that, hydrostatic pressure. Shall we do that? Anybody? Or should I take the call?
Yes, sir, you can go ahead. So you understand this, sir.
Okay, so next is, uh, you know, uh, many a times you will see some examples like, you know, uh, okay, there will be some liquid level, free surface like this, and there will be some gate at the bottom. So it will be all fluid, and this gate will be hinged at some end, and it is kept shut by applying some force. So they will ask what is the force that is required on this end. So something like this will be the ground level. So what is the force that we need to apply at the end so that this gate won't open and water won't come out? Or maybe in some cases you want that gate to open. For example, if it is a dam and if the rain is quite heavy on some particular day, so dam cannot sustain, you know, let's say this is a dam wall or something like that. So there will be some safety limit for that wall. Above that, if water level goes, it is not good for the structural strength for the strength of the dam. So then in that case, what you do, you design the gate in such a way that after certain height of the wall, after certain height of the water above the gate, let's say edge, it will open. Because the force that is applied at the gate from the water, that will, let's say f dash, that will become, f dash will become greater than f at this height, and it will open. So that is like a safety mechanism for a dam. And in some cases you may not have like you know straight gates are not possible. In some cases you may have curvatures. For example, you may have something like this arrangement. One second. Yeah, so instead of the gate at the bottom, I can just copy this thing, right? It's not copying. So instead of straight gate, I may have something like this. So this is my gate, something like curved area. It's not a straight case. So same thing here. I want this gate to open after certain height, and before that it should not open. So either it can be kept in its place by its own weight, or maybe we need to apply some force to keep it in check. But after a point when f dash becomes greater than f, it should open. So that depends on this height. So these type of questions are there in which you need to uh, do the force calculations. So what happens if it is a straight gate or vertical surface, there will be only horizontal force acting on it from fluid. But if it is a curvature like the second image that I've shown here, in that case there will be force acting. Force is always perpendicular to the curvature, right? So it will be acting in all directions. So there, what we do, we divide the F dash, or maybe the resultant of all the forces acting on that curvature. What we do, we divide it into two parts, Fy dash and Fx dash, and then we do the calculations. We take the resultant and what angle it is coming, etc., etc. So these type of questions are there. So first, we'll take the common example of vertical gate. If it is, I'll show it in some fashion like this. So this is that gate I'm talking about. And what happens? Let's say for this gate, the water level is somewhere at the top. So this is our free water level, and then this gate is submerged like this. So what happens? Because of the hydrostatic pressure, so here it is atmospheric pressure, right? So as you go down, the hydrostatic pressure will increase, and this plate will feel higher pressure than the atmospheric pressure at the bottom. But this thing, what you call, in this case, this thing, like if you consider just a vertical plate, at the top, let's say this is a height, maybe B or something, and this is the height H at the bottom. So what happens? At the top of this plate, the pressure will be P ATM plus rho G H, correct? And at the bottom, so P top, P bottom. At the bottom, it will be P atmosphere plus rho G H, which is observed till this level, till this height, and then additional pressure because of the depth B. So that will be rho G P. So it will basically PT plus rho G B. So you see the pressure is not constant on this plate, it is varying. So, and it is, if you want to show it in some, they call it as a pressure diagram. So what they do is like this. From the free surface, you draw a vertical line and you show the pressure, how it is varying. So in this case, since the free surface is here, it will be P atmospheric here, and here at this level it will be PT, and they show some direction like this, and at the bottom it will be PB at this level. You understood? So on the plate, if you see, the pressure is variable. It's not a constant pressure calculation. So in this case, we define something called as uh, the force will be it is given as 1 second. So force essentially is what you say, pressure into cross-sectional area, right? But here pressure is variable, so you cannot take it like that. So ideally you should do integration at all elemental lengths and all, but that is very difficult. And people have done some calculations, and what they observed is it will be essentially equal to rho g into the cross-sectional area and some x bar. So x bar is the vertical distance of center of gravity of plate from free surface. So this is how you get the force. But now the question is, this force acts at what point, right? So that is what is called as center of pressure. There is this new term which is called as center of pressure. And this is point of application of hydrostatic force. One important thing to note about this is imaginary. You define it. It's not a real point on the body. It's imaginary point through which the force, total hydrostatic force, acts on the body. And if I denote it by, let's say, h bar, then h bar, I mean, this formula you must have seen in the class is called as, it is given as moment of inertia about the center of gravity, cross-sectional area, x bar, and plus x bar. So the notation may be slightly off. Maybe I'm not following the professor's notation here, but you get the idea, right? This is center of pressure, and this is your center of gravity of the body, or the distance of center of gravity from the top free surface, and this is the center of pressure, distance of center of pressure from the free surface. And one thing you should note down is this ICG. It is moment of in a moment of area taken about axis parallel to free surface. Like that. And then another case is there, if this flat plate, if it is vertical, like in this case it is considered as vertical, but what if it is at some angle theta with the free surface? So in that case, this formula gets slightly modified. There will come a sine square theta term here. Other than that, it remains same. So theta is the inclination of flat surface with free surface. So see, the thing is, the important thing that I want to mention here is what happens. Yeah, one thing I mentioned, the center of pressure is imaginary point. It's not a real point. And what happens? Sometimes this question is asked in the exam that, let's say you are at very high depth. Let's say maybe like 2 kilometers down the sea level, inside the ocean, and you put a flat plate there. So the question they ask is, what if when you are going down from the top sea level to the bottom, let's say 2 kilometer, till 2 kilometer you go, what happens to the center of gravity and the center of pressure? What happens? Do they move? Do they remain at the same location, or how it goes? So that it's a very important note that center of gravity is stationary at all times. as depth increases, center of pressure moves closer to the center of gravity. So center of gravity never moves. It's a center of gravity cannot move, right? Because it is a measure of uh, mass of the plate. But center of pressure, it is a measure of total hydrostatic force that is acting on the plate. So as the h increases or the depth increases, center of pressure moves or it shifts closer to the. But it should not move. It should be shifts closer to the center of gravity. So that is important thing to note here. And one more thing to note is because typically we encounter flat plates. So for flat plate, CG is at h by 2, where h is the, or maybe I'll not use h because h is used somewhere else. In this case, I used I think B. So CG will be B by 2. CP will be 2B by 3. And this ICG, it is typically dB cube by 12. So D will be this dimension. So this numerical values and all you can do calculations there. It's not an important thing, and we don't have time also. But these things, for at least flat plate, you should remember the CP is at 2B by 3 from the top. These are all from top of the plate. So like that. Then we move on to the curved surfaces. Unfortunately, we are running out of time, so I cannot take examples at this point. But I think maybe you can go and solve some numericals. If you have any issues, you can ask me next time in the next lecture or next Tuesday. But just for the sake of completion, let me complete the curved surfaces also. So in case of curved surfaces, let's say you have a liquid level till here and you have a vertical wall, and then you have a curved surface like this, and this is the ground. So this is something like this. This is the fluid filled domain. So I'll just make it slightly thick. You should understand that this is the gate for the curved surface where you are calculating the forces. So as I told you earlier, it will have horizontal and vertical force directions, right? So for horizontal direction, what we do, we just take its projection in a horizontal plane. So if you take a projection like this, it will look something like this, right? So basically you are looking at this gate from this side. So I'm drawing an eye here. So basically looking at this gate from this side, what you see a flat plate like this, right? And then you do the usual calculations as done for the flat plate case here. In that case, your Fx will be again OG A x bar, and it will act from the CP. Understood? But in case of, so this will give you Fx, the horizontal force direction. But for vertical force direction, what you do? 1 second. Maybe I'll draw the eye here. So that, but in case of vertical force, what you do? You draw a imaginary line from the object that you are considering, the curved surface. So in this case, it will be like this. So whatever liquid is inside this object, so that will exert the force in the y direction on the beam, right? And that will be equal to the weight of the liquid in this red area, the shaded area, in shaded area, and it will act through the center of gravity of this shaded area. Okay, so let's say it comes out somewhere here. It's a like some mathematics is involved in this, but you can do the calculations, and some data is required that will be given in the question. So what happens if you consider this curved surface again separately? There will be a horizontal force acting something like this, and there will be some vertical force acting in some fashion like this, and they will act through these points mentioned here. So what you do, you take the resultant force of them, you take the vector resultant, and you get the net force acting on the gate. So its magnitude will be fx square plus fy square, and it will act through tan theta will be fy by fx, standard two vector resultant this thing. So that is there. Unfortunately, because of the time, I am not able to take example, but there are very interesting questions that can be asked from this type of this area. I will request you to go home and do some problems, and maybe next class, if you have any doubts, I'll answer them. Otherwise, we'll see, because right now we don't have time.
So one question, sir, quick question. So the material of the gate will not matter.
It will matter, but not in these calculations. It will matter when you want to consider, like, let's say if it is very light gate, it won't matter. But if it is a very heavy gate, then its own weight will act, right. It will be in downward direction, something like this, and that weight will act through the center of gravity of that gate. Na? So when you want to do the calculations, final calculations as to how much force I want to apply so that this gate won't open, at that time you need to take the moments of all these forces about some point, which is the hinge point from where the gate opens. So in that case, the gate weight you can consider, but not for the calculation of hydrostatic forces, not for this part what we discussed. Okay.
Yes, sir. Generally, so we which still gets mostly. So
Yeah. Actually, many a times this gate mass will be very high, because if you consider a dam or something, uh, the gate will easily be of 100 200 kgs, right? So there it is important to consider the gate, but not for the calculation of fx and fy, because this fx and fy are coming because of the fluid that is there present around the gate. So there it won't consider, but in the final calculations where you want to calculate the see, I told you here, right? You want to, let's say, calculate this f dash. F dash is the height at which your gate opens. So in that calculations, the mass of the gate is also should be included. So that is included there. Okay.
oh yes, sir. Yes.
Yeah, and then there is this last part. I'll just briefly give you the jinx of it. So then there is this concept called as give me 5 minutes. I know I am over time. Then there is this concept called as equilibrium conditions. So there are two type of classifications here. One is fully submerged body. So, and another is floating body. So the body is at the surface, floating. So uh, there are like cases where uh, you know uh, this I would like to I mean Right now we don't have much time, so I think I'll stop here. Maybe in next class I'll spend some time on these concepts. But right now I think we are over time, so I think I should better stop here. So
So we have a
uh,
question that hinge is in the on the top, sir. Hinge is at the top. There is a question. Actually, I'll just show you the question it next, sir. Next at the next time. Yeah.
yeah. Actually, I should have taken some problem on this part, but unfortunately not now. Maybe next time you come to the class early, 5-10 minutes. I start the class like 10 minutes early. Nobody comes up. So maybe in that time we can discuss along with the next class's content. But this equilibrium conditions I'll take it up next time. Maybe 5-10 minutes I'll spend on this
Sure.
because
Definitely.
I cannot complete this time now.
Yeah.
Okay.
Yeah. Thank you,
So
sir. Thank you very much.
yeah, thank you everyone. We'll stop now, and maybe next time we'll see each other. Sharif, thank you, and yeah, I'll stop the presentation now and see you next time. Good night.